Hello there, my name is Ilara, and welcome to the Late Night Science Channel. Tonight we're going to talk about something that sounds simple, but when you actually sit down and think about it, when you really try to wrap your mind around what it means, it changes everything. A light year. You've heard this term before, probably hundreds of times, maybe thousands. Scientists say it all the time when they talk about space, about stars, about distant galaxies. But here's the thing most people don't realize, and I mean really realize deep down. When you understand what a light year actually is, when you truly grasp the distance it represents, it fundamentally shifts how you see the universe, how you see your place in it, how you see everything around you. So if you enjoy this kind of deep, peaceful exploration into the cosmos, go ahead and subscribe to the channel. It really helps me create more content like this. And now, let's begin this journey together. Let's start with something you know, something familiar: distance. You understand distance in your everyday life, right? You know how far it is to walk to the corner store, maybe 10 minutes at a normal pace. You know the drive to work, perhaps 20 minutes if traffic's good, maybe 40 if it's not. You know the distance to the next town over, the next city, maybe a couple hours by car. These are distances that make sense to you because you've experienced them, you've traveled them, you have a feeling in your body for what they mean. A kilometer, that's about the distance you can walk in, say, 10 to 12 minutes if you're not rushing. It's a distance you can picture in your mind. You can imagine the journey, the things you might see along the way, the time it would take. These measurements, kilometers, miles, they work perfectly for our daily lives. If someone tells you the grocery store is 5 kilometers away, you immediately have a sense of what that means. You know roughly how long it'll take to drive there, maybe 7 or 8 minutes depending on the road. You can picture the route in your mind, the turns you'll make, the landmarks you'll pass. The distance is concrete, it's real, it connects to your experience of the world. When someone says a city is 200 kilometers away, you can plan accordingly. That's about 2 hours of driving, maybe 2.5. You'll want to make sure you have enough gas, maybe bring some water, plan for a rest stop if you need one. These distances fit into your life, into your understanding of space and time. We evolved to understand these kinds of distances. Our ancestors needed to know how far it was to the next water source, how far to the hunting grounds, how far they could walk in a day before needing to find shelter. Our brains developed to handle distances we could see with our eyes, distances we could travel with our legs. We didn't evolve to comprehend anything larger than that. For most of human history, these were the only distances that mattered. But then, these measurements start to break down when we talk about really large distances. The distance from New York to Los Angeles, for example, is about 4,500 kilometers. That's still manageable as a number. You can understand it in terms of a flight, about 5 hours in the air. People make that journey all the time. They cross the entire continent, watching the landscape change from eastern cities to Midwestern plains to Rocky Mountains to southwestern deserts and finally to the Pacific coast. It's a long journey, sure, but it's achievable. It's within human capability. You can imagine making that trip. The Earth's circumference at the equator is about 40,075 kilometers. Now that's a big number, but it's still something we can work with conceptually. Early explorers sailed around the world, so we know it's possible to travel that distance, even if it takes months to do it. Ferdinand Magellan's expedition took 3 years to circumnavigate the globe from 1519 to 1522. Modern commercial flights could circle the Earth in about 45 hours if you could somehow book connecting flights that went all the way around. The Earth is large from our perspective standing on its surface, but it's not incomprehensibly large. It's a finite sphere that you could, in theory, explore completely, given enough time. But now, let's go bigger. The distance from Earth to the Moon is about 384,000 kilometers, and this is where normal measurements start to feel inadequate. 384,000 kilometers. That's hard to visualize in any meaningful way, isn't it? It's not like driving across a country. It's not like sailing around the world. It's something completely different. There's no road to follow, no landmarks to pass, no scenery changing along the way. It's just distance, pure distance across empty space. How would you even begin to comprehend traveling that far? The Apollo astronauts took about 3 days to travel from Earth to the Moon, using some of the most powerful rockets ever built, rockets that accelerated them to about 11 kilometers per second. That's roughly 39,600 kilometers per hour. To put that in perspective, that's about 400 times faster than highway driving. Think about that for a moment. 400 times faster than the fastest you've ever driven on a highway. And even at that incredible speed, which required enormous rockets burning massive amounts of fuel, it still took 3 full days. 3 days of traveling through empty space at speeds no human had ever experienced before, just to reach our nearest celestial neighbor. And here's the thing that really puts it into perspective. The Moon is so close, relatively speaking, that you can see it with your naked eye. You can see details on its surface with just a pair of binoculars. It's right there, hanging in the sky above you. And yet it takes 3 days of rocket travel to reach it. When we start talking about the distance to other planets, to the Sun, to other stars beyond our solar system, kilometers become completely useless. The numbers get so large they lose all meaning. They stop being distances you can relate to and just become abstract symbols on a page. The distance from Earth to the Sun, our own star, the one we orbit, the source of all light and heat that makes life possible on our planet, is about 150 million kilometers. Try to visualize that. You can't, can you? Your brain just sees a really big number, but you don't have any intuitive sense of what it means. There's nothing in your daily experience that prepares you for a distance like that. Nothing in human evolution equipped us to understand distances this vast. We evolved to understand the distance to the next hill, the next valley, the distance we could walk before sunset. We didn't evolve to understand 150 million kilometers. The Apollo spacecraft that carried astronauts to the Moon traveled at about 11 kilometers per second on average. At that speed, it would take about 160 days, over 5 months, to reach the Sun's distance. And that's using some of the fastest spacecraft technology we had in the 1960s and 70s. The fastest spacecraft humans have ever built, the Parker Solar Probe, travels at speeds up to 192 kilometers per second when it's close to the Sun, using its gravity to slingshot itself to higher and higher velocities. Even at this incredible speed, which is about 17 times faster than the Apollo spacecraft, the probe still takes months to complete its orbits around the Sun. And the Sun is close. It's right here in our cosmic neighborhood. It's the star we orbit. We see it every single day. It's familiar to us. And yet it's 150 million kilometers away, a distance so vast that even our fastest spacecraft takes months to traverse it. When we start talking about distances to other stars, even the Sun's distance becomes tiny by comparison. The Sun is our nearest star, and it's 150 million kilometers away. The next nearest star, Proxima Centauri, is about 266,000 times farther than that. 266,000 times farther than a distance that already takes our fastest spacecraft months to cover. Let that sink in for a moment. This is exactly why astronomers needed a different unit of measurement, not because they wanted to make things complicated, not because they enjoyed confusing people with big numbers, but because kilometers simply don't work when you're measuring cosmic distances. Using kilometers to measure distances to stars would be like using millimeters to measure the distance between countries. Technically possible, sure, but completely impractical. The numbers become so large, they lose all meaning. They stop being distances and become just numbers, abstract mathematical concepts that don't connect to anything in our lived experience. So astronomers came up with something different, the light year. But here's what you need to understand right from the start, and this trips up a lot of people. A light year is not a measure of time. I know it has the word year in it, which makes it sound like time, but it's not. A light year is a measure of distance. It's the distance that light travels in 1 year. Pure distance, not time. Now, why base a measurement on light? Well, because light is special. Light is the fastest thing in the entire universe. Nothing, and I mean absolutely nothing, can travel faster than light. This isn't a speed limit we haven't figured out how to break with better technology or more powerful engines. It's a fundamental law of physics, woven into the very fabric of the universe itself. The speed of light is a constant, unchanging, the same everywhere in the universe. Whether you're on Earth, on Mars, in another galaxy, or at the edge of the observable universe, light always travels at the same speed. Light travels at about 300,000 kilometers per second. Let me say that again slowly because it's important. 300,000 kilometers per second. Every single second, light travels 300,000 kilometers. This isn't an approximation or a rough estimate. It's been measured with extraordinary precision. The exact value is 299,792.458 kilometers per second, but for our purposes tonight, 300,000 kilometers per second is close enough to work with. That's incredibly fast. To put it in perspective, light can travel around the Earth's equator about 7.5 times in just 1 second. In the time you snap your fingers, about half a second or so, light could circle the entire planet multiple times. In 1 second, light could travel from New York to Los Angeles and back about 37 times. It's a speed that's almost impossible to visualize because nothing in our everyday experience moves anywhere near that fast. The fastest thing most people experience regularly is probably an airplane. A commercial jet flies at about 900 kilometers per hour, or about 0.25 kilometers per second. Light is almost 1,000 times faster than that. The fastest car ever built, the Thrust SSC, reached about 1,200 kilometers per hour, or about 0.33 kilometers per second. Light is about 900,000 times faster than that. Even the fastest spacecraft we've built, the Parker Solar Probe at its peak at 192 kilometers per second, is still only about 0.064% the speed of light. It's moving incredibly fast by human standards, but compared to light, it's crawling. When you flip on a light switch in your room, the light reaches your eyes essentially instantly because the room is so small. The light travels from the bulb to your eye in about 10 billionths of a second. That's so fast, there's no perceptible delay. As far as your brain is concerned, the light appears the instant you flip the switch. But the light did travel. It took time. It's just that the time was so incredibly short you couldn't possibly notice it. When you look at the sun in the sky, you're actually seeing it as it was 8 minutes and 20 seconds ago. That's how long light takes to travel from the sun to Earth. The sun is so far away that even light, traveling at 300,000 kilometers per second, needs over 8 minutes to cover the distance. This has an interesting implication that most people don't think about. If something happened on the sun right now, if it suddenly changed color or dimmed or even exploded, we wouldn't know for over 8 minutes. the event would happen, but the light carrying information about that event would still be traveling towards us through space. We'd keep seeing the sun as it was, not as it is, for over 8 minutes. When you look at the moon at night, you're seeing it as it was about 1.3 seconds ago. Not much of a delay, but still a delay. When the Apollo astronauts walked on the moon and talked to mission control on Earth, every word they spoke took 1.3 seconds to reach Earth, traveling as radio waves at the speed of light. And every response from mission control took another 1.3 seconds to reach the moon. This created a nearly 3-second gap in every exchange. You can actually hear this delay if you listen to the recordings. There's always this pause, this lag, because the radio signals carrying their voices had to travel at the speed of light across the distance between Earth and the moon. Light doesn't travel instantly, it has a speed, and that speed, while incredibly fast, is still finite, still limited. This is one of the most important discoveries in the history of physics. Before the late 1600s, most people assumed light traveled instantly. You opened your eyes and you saw things immediately, so it seemed like light must be instantaneous, appearing everywhere at once with no travel time. But in 1676, a Danish astronomer named Ole Romer made a careful observation of Jupiter's moons and noticed something strange. The times when the moons disappeared behind Jupiter varied depending on where Earth was in its orbit around the Sun. When Earth was closer to Jupiter, the eclipses happened earlier than predicted. When Earth was farther from Jupiter, they happened later. Romer realized this was because light took time to travel the different distances. He calculated that light took about 22 minutes to cross the diameter of Earth's orbit. His calculation wasn't quite right because he didn't know the exact size of Earth's orbit at the time, but he proved something revolutionary, that light has a finite speed. It doesn't travel instantly. Today, we know the speed of light with extraordinary precision. We've measured it using lasers, atomic clocks, and sophisticated equipment. We've confirmed that it's constant, that it doesn't change depending on how fast you're moving or where you are in the universe. And we've discovered that this speed, this constant, is woven into the very fabric of reality itself. It's not just the speed that light happens to travel at. It's a fundamental property of space-time, the underlying structure of the universe. So a light year is the distance light travels in 1 year at this speed. Let's calculate that together. Light travels at 300,000 kilometers per second. There are 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, and 365 days in a year. If we multiply all of these together, 300,000 times 60 times 60 times 24 times 365, we get approximately 9.46 trillion kilometers. To be more precise, it's 9,460,730,472,580.8 kilometers. But for simplicity, we usually just say 9.46 trillion kilometers. That's what a light year is, 9.46 trillion kilometers. Not a measure of time, but a measure of distance. The distance that light, the fastest thing in the universe, travels in 1 full year, moving at 300,000 kilometers every single second for 365 days straight. And that's the number we're going to try to understand tonight, because understanding what a light year means is essential to understanding our place in the universe, the distances between stars, the true scale of the cosmos we live in. But first, we need to talk about what a trillion actually means, because most people, if we're being honest, have no intuitive sense of how large this number really is. We use words like million, billion, and trillion in everyday conversation without really thinking about what they mean. We hear about government budgets in the trillions, we hear about billionaires, we hear about millions of people. but we don't really understand the massive differences between these numbers. They all sound like big numbers to our ears, so we treat them as roughly equivalent in our minds, but they're not. The differences between them are staggering, almost incomprehensible. A million is 1,000 millions. Now we're jumping up by a factor of 1,000. If you saved $1 every single second, not every day, but every single second without stopping, you'd need about 32 years to save $1 billion. That's more than the time it takes for a generation to grow up and mature. If you started counting seconds when you were born and counted continuously without sleeping, eating, or taking any breaks whatsoever, you'd be 32 years old when you finally reached $1 billion. Think about that for a moment. 1 million seconds is about 11 and a half days. That's conceivable. You can imagine a period of 11 and a half days. It's less than 2 weeks. But 1 billion seconds is 32 years. The jump from 1 million to 1 billion is enormous, almost unimaginable in scale. 1 trillion is 1,000 billions, and here's where numbers start to completely lose their connection to anything we can relate to in our daily lives. If you counted to 1 trillion, counting one number per second without ever stopping, it would take you about 31,700 years. Let me put that in perspective for you. That's longer than all of recorded human history. Agriculture, the foundation of all civilization, was only invented about 10,000 years ago. Before that, all humans everywhere lived as hunter-gatherers, moving from place to place, following animal herds and seasonal plants, never settling down permanently. Writing systems first appeared about 5,000 years ago in ancient Mesopotamia. The pyramids of Egypt were built about 4,600 years ago. The wheel, one of humanity's most important inventions, was probably invented about 5,500 years ago. To count to 1 trillion, you'd need to have started counting before any of that happened. You'd need to have started when humans still lived in small tribal groups scattered across the landscape, when there were no cities, no nations, no written language, no agriculture, no permanent settlements of any kind. You'd need to have been counting through the entire span of human civilization, through every invention, every discovery, every empire that rose and fell, through every war, every peace, every triumph and tragedy in all of human history. And you'd still be counting today, right now, and you'd still have thousands of years to go before you finally reached 1 trillion. Let me try to make this even more concrete, even more tangible. 31,700 years ago, modern humans were living in the last ice age. We were using stone tools, sharp rocks tied to wooden handles. We were hunting woolly mammoths and giant ground sloths, massive animals that no longer exist. We had barely begun to spread across the globe. Modern humans had only recently left Africa and were just starting to populate Europe and Asia. There was no complex language as we know it today, no art beyond the most primitive cave paintings on rock walls, no technology beyond sharp stones and wooden spears. That's how far back 1 trillion seconds takes you. And a light year is 9.46 trillion kilometers. Every single one of those kilometers is a real distance, not an abstract unit. It's the distance you could walk in about 10 to 12 minutes at a normal, comfortable pace, the distance from your home to the local store, perhaps. And there are 9.46 trillion of those individual kilometers in one light year. 9.46 trillion separate, distinct kilometer-long segments, each one the length of a short walk down the street. So when we say a light year is 9.46 trillion kilometers, we're talking about a distance that absolutely dwarfs anything in our daily experience. You can write it down on paper, you can calculate with it, you can use it in equations, but grasping it intuitively, really feeling what it means is nearly impossible. Our brains simply didn't evolve to handle numbers this large. We evolved to count the number of people in our tribe, maybe 30 or 40 individuals, the number of animals in a herd, perhaps a few dozen, the number of days until the seasons change, maybe 90 or 100. We can count to a few hundred, maybe a few thousand if we really concentrate and focus, but 9.46 trillion? That's so far beyond our cognitive capabilities that it might as well be infinity to our primitive human brains. The best way to understand a light year, really understand it, is to build up to it gradually, starting with distances we can comprehend and scaling up step by step, watching as distances that seem vast become tiny compared to what comes next. We're going to take this journey slowly, peacefully, moving from the familiar to the unfamiliar. Let's start with 1 light second, 300,000 kilometers. That's about the distance from Earth to the Moon, and then about 3/4 of the way back. Think about what that means for a moment. Light leaves Earth, travels all the way to the Moon, which is 384,000 kilometers away, bounces back toward Earth, and gets about 3/4 of the way home. And all of that happens in 1 second, 1 single second. When astronauts on the Moon talked to Mission Control in Houston during the Apollo missions, there was this communication delay of about 1.3 seconds each way. The astronauts would say something, and Mission Control wouldn't hear it for 1.3 seconds because the radio signal, traveling at the speed of light, needed that long to make the journey through space. When Mission Control replied, their response took another 1.3 seconds to reach the Moon. So every exchange, every back and forth had a nearly 3-second delay built into it. It's subtle when you listen to the old recordings, but it's always there. There's this pause, this slight lag, because of the distance the signals had to travel, and because nothing, not even radio waves, can travel faster than light. 1 light minute is 60 light seconds, 18 million kilometers. The Sun is about 8 light minutes away from Earth, which works out to about 150 million kilometers. So 1 light minute is roughly 12% of the distance from Earth to the Sun. If you could somehow stand on the surface of the Sun, which obviously you can't because it's a ball of superheated plasma with a surface temperature of about 5,500 degrees Celsius, but if you could somehow stand there and look at Earth, you'd be seeing Earth as it was 8 minutes and 20 seconds ago. If Earth suddenly exploded right now, you wouldn't know for over 8 minutes. The event would happen, the planet would be destroyed, but the light from that catastrophic event, carrying the information about it, would take over 8 minutes to cross the distance between Earth and the Sun. This has practical implications for space exploration that most people never think about. When NASA operates rovers on Mars, there's always a communication delay because Mars is so far away from Earth. At its closest approach, when Earth and Mars are on the same side of the Sun in their respective orbits, Mars is about 32 million kilometers from Earth, which is about 2 light minutes. At its farthest, when Earth and Mars are on opposite sides of the Sun, the distance is roughly 400 million kilometers, roughly 22 light minutes. This means when the Perseverance rover is operating on the Martian surface, every command sent from Earth takes between 2 and 22 minutes to arrive, depending on where Mars is in its orbit at that moment. And any data the rover sends back, any photographs or measurements, takes the same amount of time to reach Earth. You can't drive a rover on Mars in real time like you'd drive a remote-controlled car in your backyard. The delay is too long. The lag makes it impossible. Instead, NASA engineers have to plan the rover's activities very carefully. They analyze images from previous days, plan out a route, write a detailed sequence of commands telling the rover exactly what to do, send those commands to Mars, and then wait. If something goes wrong, if the rover gets stuck on a rock or encounters an unexpected obstacle, they can't react instantly. They have to wait for the information to reach Earth, which takes anywhere from 2 to 22 minutes, depending on orbital positions. Then they have to analyze what went wrong, figure out a solution, write new commands, send those commands back to Mars, and wait another 2 to 22 minutes for them to arrive at the rover. A problem that might take 30 seconds to solve with a remote-controlled car on Earth can take an hour or more on Mars because of the speed of light delay. 1 light hour is 60 light minutes. That's about 1,080,000,000 kilometers. Over 1,000,000,000 kilometers. That's a distance so vast that even imagining it becomes difficult. The planet Saturn, at its closest approach to Earth, is about 1.2 light hours away. Saturn, one of the most distant planets you can see with your naked eye from Earth, a beautiful ringed world that's been observed and wondered about since ancient times, is about 1.2 light hours away. When the Cassini spacecraft was orbiting Saturn from 2004 to 2017, taking those incredible close-up photographs of the planet and its moons that we've all seen, there was over an hour of delay between when it took a picture and when that picture finally reached Earth. The spacecraft would take a photo, convert it to digital data, transmit it as a radio signal traveling at the speed of light through space, and over an hour later, scientists on Earth would receive it and see what Cassini had photographed. This meant that Cassini couldn't be controlled in real time by human operators. Engineers and scientists on Earth couldn't watch what the spacecraft was seeing through its cameras and adjust its path on the fly like you might steer a car or pilot a drone. Instead, they had to program entire sequences of commands days or even weeks in advance, upload them to the spacecraft's computer, and trust that Cassini would execute them correctly when the time came. If something went wrong during a maneuver, the spacecraft had to be smart enough to handle it autonomously, to recognize the problem on its own and switch to a safe mode. Because by the time the problem was reported back to Earth and new commands could be sent, over 2 hours would have passed. The situation could have changed completely in that time. The spacecraft could have crashed or been damaged beyond repair. 1 light day is 24 light hours, about 25,900,000,000 kilometers. Now we're entering a region where nothing human-made has ever been, and nothing will be for decades or perhaps centuries to come. This is deep space, far beyond all the planets, far beyond anything we've directly explored with our spacecraft. Out here, the sun would no longer appear as the overwhelming source of light and heat it is from Earth. It would appear as just a bright star, brighter than other stars, certainly, but just a point of light in the darkness of space. If you were somehow out here, floating in space at 1 light week from the sun, you'd see the sun as a brilliant star in the sky, but you'd also see thousands of other stars scattered across the black void of space. You'd realize, perhaps for the first time, that the sun is just one star among countless others, nothing special from a cosmic perspective. 1 light month is roughly 30 light days, about 778 billion kilometers. Now we're entering a region where nothing human-made has ever been, and nothing will be for decades or perhaps centuries to come. This is deep space, far beyond all the planets, far beyond anything we've directly explored with our spacecraft. Out here, the sun would no longer appear as the overwhelming source of light and heat it is from Earth. It would appear as just a bright star, brighter than other stars, certainly, but just a point of light in the darkness of space. If you were somehow out here, floating in space at 1 light week from the sun, you'd see the sun as a brilliant star in the sky, but you'd also see thousands of other stars scattered across the black void of space. You'd realize, perhaps for the first time, that the sun is just one star among countless others, nothing special from a cosmic perspective. 1 light year is 365 light days, it's 12 light months, it's 52 light weeks, it's 8,760 light hours, it's 525,600,000 light seconds. See how quickly the numbers scale up? We started with 1 light second, which was already an enormous distance by human standards, about the distance from Earth to the Moon and most of the way back. And we've been multiplying by larger and larger numbers: 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, 7 days in a week, 30 days in a month, 12 months in a year. And we're just now getting to 1 light year. 9.46 trillion kilometers. That's the distance light travels in 1 full year, moving at 300,000 kilometers every single second for 365 days straight without stopping. And this is the fundamental unit astronomers use to measure the distances between stars. Because stars are separated by distances measured in light years, and nothing smaller makes any sense when you're dealing with these vast cosmic scales. So why do astronomers use light years? Because every other option is worse, far worse. Imagine if astronomers used kilometers for everything they talked about. Proxima Centauri, the nearest star to our sun, is about 40,140,000,000,000 kilometers away. That's awkward, hard to remember, and doesn't give you any intuitive sense of the distance at all. It's just a huge number with lots of zeros. But if I tell you Proxima Centauri is 4.24 light years away, that's cleaner, more elegant. You can compare it to other distances more easily. If one star is 4 light years away and another is 40 light years away, you immediately know the second one is 10 times farther without having to do any complicated math. The ratio is obvious. Light years also connect distance and time in a useful way that helps us understand what we're seeing. When you look at a star that's 4 light years away, you're seeing light that left that star 4 years ago. You're looking into the past. You're seeing that star not as it is right now, in this present moment, but as it was 4 years ago. This connection becomes crucial when studying the universe, when trying to understand cosmic history and evolution. The speed of light isn't just fast, it's the speed limit of the entire universe. Nothing can go faster. And this isn't a technological limitation that we might overcome someday with better engineering or more powerful rockets or some clever trick we haven't thought of yet. It's a fundamental law of physics built into the very structure of space-time itself, the fabric of reality. The speed of light isn't just a speed. It's a cosmic constant that defines the relationship between space, time, energy, and matter. Einstein's theory of special relativity, published back in 1905, showed that as objects approach the speed of light, strange things start to happen. And these aren't just theoretical predictions on paper. They're observed facts, confirmed by countless experiments over the past century and counting. Time slows down for the moving object relative to stationary observers. This is called time dilation, and it's been measured directly many times. The object's mass effectively increases, or more precisely, its inertia increases. It becomes harder and harder to accelerate the object as it goes faster. The amount of energy required to accelerate it increases without limit as you approach light speed. To actually reach the speed of light would require infinite energy, which is impossible. The universe doesn't contain infinite energy. Therefore, nothing with mass can ever reach the speed of light, let alone exceed it. Let me explain why this happens, why the universe works this way. In our everyday experience, if you're on a train moving at 50 kilometers per hour and you throw a ball forward at 20 kilometers per hour relative to the train, someone standing on the ground watching would see the ball moving at 70 kilometers per hour. The speeds just add together. This seems obvious, and it works perfectly well for everyday speeds that we're used to. But Einstein showed that this simple addition doesn't work when you're dealing with speeds close to the speed of light. If you're on a spacecraft moving at half the speed of light and you shine a flashlight forward, you might think the light would move at 1.5 times the speed of light, at least from the perspective of someone watching you from outside the spacecraft. But it doesn't. The light still moves at exactly the speed of light, 300,000 kilometers per second, both from your perspective on the spacecraft and from the perspective of someone watching you from outside. This seems impossible at first. How can the light be moving at the same speed for both observers when one observer is already moving at half the speed of light relative to the other? The answer is that space and time themselves adjust to keep the speed of light constant. If you're moving very fast, time literally runs slower for you from the perspective of a stationary observer, and distances in the direction you're moving actually contract, become shorter. These aren't optical illusions or measurement errors or tricks. They're real physical effects happening to space and time themselves. Space and time are not absolute, not fixed. They're relative, depending on your motion through the universe. The only thing that's absolute, that's the same for everyone, regardless of how they're moving, is the speed of light. Light always moves at 300,000 kilometers per second for every observer, no matter what. This has been tested experimentally countless times in particle accelerators around the world. Particles in these accelerators are accelerated to speeds very close to the speed of light, sometimes reaching 99.999% of light speed. We can measure how long these particles live before decaying into other particles, and we consistently find that particles moving at 99.9% of the speed of light live much longer than identical particles at rest in the laboratory. Time is literally moving slower for them. This isn't theory anymore. It's measured fact, repeated thousands of times in laboratories around the world. Cosmic rays, high-energy particles from space, create muons when they hit the upper atmosphere. Muons are subatomic particles that decay very quickly, with a half-life of about 2 microseconds. At this decay rate, even moving at close to the speed of light, muons created in the upper atmosphere shouldn't be able to reach the ground before decaying into other particles. The math just doesn't work out. And yet, we detect muons at ground level all the time. Detectors on the surface of the Earth consistently register these particles. Why? Because from our perspective on the ground, the muons are moving so fast that time dilation extends their lifetime dramatically. What's 2 microseconds from the muon's perspective becomes much longer from our perspective on Earth, long enough for them to reach the ground before decaying. We can measure this. We can count the muons. The numbers match the predictions of relativity perfectly. Only massless particles, particles with no rest mass, like photons, which are the particles of light, can travel at the speed of light. Photons have no mass, so they don't need infinite energy to reach light speed. In fact, photons must always travel at light speed. They can't slow down or speed up. From the moment they're created, perhaps in the heart of a star or in a light bulb, to the moment they're absorbed, perhaps by your eye or by a solar panel, they travel at exactly the speed of light. No faster, no slower. This is simply what photons do. It's their fundamental nature built into what they are. This has profound implications for space travel that go far beyond just engineering challenges or technological hurdles. Even if we developed perfect propulsion systems with access to unlimited energy, even if we solved every single engineering problem imaginable, we still couldn't travel faster than light. It's not possible. The 4.24 light-years to Proxima Centauri represents a minimum travel time of 4.24 years, even in the most optimistic scenario where we could somehow accelerate a spacecraft to nearly the speed of light, which itself would require more energy than we can currently imagine producing. And that's just getting to the nearest star. Most destinations in space are much, much farther away. The interesting places, the places we might want to explore, could be dozens or hundreds or thousands of light years distant. Some science fiction stories propose ways around this limitation, warp drives that somehow bend space around a spacecraft, allowing it to effectively travel faster than light without actually moving faster than light through space. Wormholes that create shortcuts through space-time, connecting distant points in space through a tunnel. Hyperspace, some kind of alternate dimension where the laws of physics are different and faster-than-light travel becomes possible. These are creative ideas, and I'll admit, some of them, like warp drives, have a basis in theoretical physics. The Alcubierre drive, proposed back in 1994, is a theoretical solution to Einstein's field equations that would allow faster-than-light travel by contracting space in front of a spacecraft and expanding it behind. It's mathematically consistent with general relativity. But there are serious problems with all of these ideas. The Alcubierre drive would require exotic matter with negative energy density to work. No such matter is known to exist anywhere in the universe. Some physicists think it might be fundamentally impossible on basic physical grounds. Even if exotic matter does exist somewhere, you'd need an enormous amount of it, possibly more mass energy than exists in the entire observable universe, just to move one small spacecraft. And there are causality problems with the concept. If you could travel faster than light in this way, you could potentially travel backward in time, creating all sorts of logical paradoxes. Wormholes, if they exist at all, would likely be incredibly unstable and would collapse almost immediately, long before anything could pass through them. Keeping a wormhole open long enough to travel through it might require more energy than exists in the entire universe. And again, there are causality problems. If wormholes allow faster-than-light travel, they also potentially allow time travel to the past, with all the associated paradoxes that entails. Hyperspace is pure speculation, with absolutely no basis in known physics. It's a science fiction concept that makes for entertaining stories, but doesn't have any connection to real physics or mathematics. There's no evidence that any such thing exists or could exist. It's entirely imaginary. As far as we know, based on over a century of careful experiments and observations and theoretical work by thousands of brilliant physicists, the speed of light is an absolute barrier. It's not a challenge to be overcome with better technology someday. It's a fundamental law of nature, as unchangeable as the fact that circles are round or that 2 + 2 = 4. When we talk about stars that are hundreds or thousands of light years away, we're talking about distances that might be fundamentally unreachable with any technology that's consistent with the laws of physics as we currently understand them. The light year doesn't just measure distance, it measures a barrier, a limit, a boundary beyond which the normal rules of cause and effect start to break down in strange ways. Let's talk about Proxima Centauri specifically, because it's our closest stellar neighbor, and it helps us understand these distances in a more practical, concrete way. Proxima Centauri is a small red dwarf star in the Alpha Centauri system, which is actually a triple star system, 3 stars bound together by gravity. 2 of them, Alpha Centauri A and B, are Sun-like stars orbiting each other every 79.9 years in a slow gravitational dance that's been going on for billions of years. If you could see them up close, Alpha Centauri A and B would look like 2 suns slowly circling each other against the darkness of space. Proxima Centauri is much smaller than these two, about 1/8 the Sun's mass and 1/7 its diameter. It's so small and dim that you can't see it with your naked eye from Earth. Even though it's our nearest stellar neighbor, closer than any other star, you need a telescope to spot it. It's just too faint for the human eye to detect. Red dwarfs like Proxima Centauri are actually the most common type of star in the galaxy, making up about 70% of all stars. But they're all so dim that none of them are visible to the naked eye, despite being relatively common. When you look up at the night sky with just your eyes, every single star you can see is either larger and brighter than the Sun, or it's not actually a star, but a planet like Venus or Jupiter. Proxima Centauri is 4.24 light-years away, about 40,140,000,000,000 kilometers. That's 40 with 12 zeros after it. To put this in perspective, if you could somehow travel at the speed of the fastest spacecraft humans have ever built, the Parker Solar Probe, at 192 kilometers per second, it would take you about 6,800 years to reach Proxima Centauri. 6,800 years. That's longer than all of recorded human history. Writing was invented about 5,000 years ago. You could have started your journey once humans first learned to write, when they first began recording their thoughts and stories and knowledge on clay tablets, traveled continuously at the fastest speed any human spacecraft has ever achieved, and you'd still be traveling today, still thousands of years away from your destination. You wouldn't even be halfway there yet. There have been proposals for faster spacecraft over the years. The Breakthrough Starshot initiative, announced back in 2016 by physicist Stephen Hawking and entrepreneur Yuri Milner, proposes using powerful ground-based lasers to accelerate tiny spacecraft to about 20% of light speed. The concept is elegant and based on real physics, at least in principle. You build a spacecraft that's essentially a computer chip with a camera, weighing maybe a gram, perhaps even less, attached to an ultra-thin light sail made of highly reflective material, perhaps only a few atoms thick. Then you point massive arrays of lasers at it from Earth. The laser light pushes on the sail, and because the spacecraft is so incredibly light, barely weighing anything at all, it can be accelerated to tremendous speeds through pure light pressure. At 20% of light speed, which works out to about 60,000 kilometers per second, a probe could reach Proxima Centauri in about 20 years. Add another 4 years for the signals to travel back to Earth at light speed, and you could potentially get data from Proxima Centauri in 24 years from launch. That's within a human lifetime, which is genuinely exciting. You could launch a mission when you're young, maybe in your 20s or 30s, and potentially see the results before you die, perhaps in your 50s or 60s. But the engineering challenges are enormous, perhaps insurmountable with current or even near-future technology. First, you need incredibly powerful lasers. The proposal calls for a laser array with a total power of about 100 gigawatts. That's roughly the output of 100 nuclear power plants. All of that energy focused into a laser beam a few kilometers wide. This beam would need to track the tiny spacecraft as it accelerates away from Earth, keeping the light precisely focused on the sail. Any deviation, any slight wobble or misalignment, and the sail would drift out of the beam and the acceleration would stop, leaving the spacecraft coasting at whatever speed it had reached. Second, the spacecraft needs to survive the journey through interstellar space. At 20% of light speed, you're moving at 60,000 kilometers per second. At this incredible speed, collisions with even tiny particles become catastrophic. A speck of dust, something far smaller than a grain of sand, hitting the spacecraft at this speed would release energy equivalent to a large bomb. The spacecraft would be obliterated instantly. The spacecraft would need some kind of shielding to protect it from these collisions, but any shielding adds weight, and weight is the absolute enemy when you're trying to accelerate something using just light pressure. The more the spacecraft weighs, the more power you need to accelerate it, and the equation gets worse and worse as you add weight. It's a vicious cycle. Third, you need to be able to communicate with the spacecraft over 4 light-years of distance. The tiny probe would need a laser or radio transmitter powerful enough to send data back to Earth from 4.24 light-years away. At that distance, any signal spreads out enormously as it travels through space. The power needed to send a detectable signal across that distance is substantial, and you have to fit this capability into a spacecraft the size of a computer chip. It's like trying to shout across an ocean and be heard clearly on the other side. The physics works against you. Fourth, you need to actually hit Proxima Centauri's star system and fly past it at the right distance and angle to collect useful data. At 20% of light speed, the spacecraft is traveling so unbelievably fast that it crosses the entire orbit of Mars in about 40 minutes. The entire width of our solar system, from the Sun out to Neptune, is crossed in about 6 hours. You get one shot at this. There's no slowing down, no second chances, no course corrections once you're up to speed, because slowing down would require just as much energy as speeding up did, and you don't have that energy available in a spacecraft weighing a gram. The spacecraft flies past Proxima Centauri at 60,000 kilometers per second, has maybe a few hours, at most a few days when it's close enough to take useful pictures and measurements, and then continues on into the void beyond, never to be seen or heard from again, drifting through interstellar space essentially forever. So while breakthrough starshot is an interesting concept, and it's based on real physics rather than pure science fiction, it remains highly theoretical. The technology doesn't exist yet, and there are formidable challenges that might prove impossible to overcome. Even if we somehow built such a craft and successfully sent it tomorrow, assuming everything went perfectly, it would be at least 20 years before it reached Proxima Centauri, and another 4 years before we got any data back. That's a 24-year round trip for information, assuming absolutely everything works perfectly, which in the entire history of space exploration has never been a safe assumption. Things go wrong, systems fail, the unexpected happens. And this is just to reach our nearest stellar neighbor, the closest star to our Sun. With technology we can actually build today, the kind of spacecraft we know how to engineer and launch with current rockets and current materials and current computer systems, getting to Proxima Centauri would take not decades, but millennia. We'd need to build multi-generational spacecraft, massive vessels that could support human crews for thousands of years. The people who finally arrived at Proxima Centauri would be the distant descendants of those who launched, perhaps hundreds of generations removed, living in a world, a ship they'd never left, traveling to a destination they'd only heard about in stories passed down through the centuries from their ancestors. When you look up at the night sky on a clear evening, you're seeing stars at various distances, and you're seeing them as they were years or even centuries ago. This is one of the most profound implications of the light year, one that really changes how you think about space and time. Distance and time become inseparable when you look at the stars. You cannot separate where something is from when you're seeing it. They're linked together fundamentally. Light travels at a finite speed. It's incredibly fast, the fastest thing in the universe, but it's not instantaneous. When light leaves a star and travels through the emptiness of space toward Earth, that journey takes time, and during that time, things can change. The star might change brightness, it might change color as it ages, it might even explode in a supernova. By the time the light reaches your eyes tonight, the star you're seeing might be completely different from how it is right now in the present moment, or it might not even exist anymore at all. Sirius, the brightest star in the night sky, impossible to miss if you know where to look, is 8.6 light years away. When you look at Sirius tonight, you're seeing light that left that star 8.6 years ago. You're seeing Sirius as it was when you were 8.6 years younger. If you're 20 years old right now, you're seeing Sirius as it was when you were about 11, probably in middle school. If you're 40, you're seeing it as it was when you were in your early 30s. The Sirius you see tonight is Sirius from the past, not Sirius as it exists right now in this present moment somewhere out there in space. Now, Sirius is a stable main sequence star. It's not going to change much over a few years or even a few decades. Stars change very slowly from a human perspective, evolving over millions or billions of years rather than years or decades. But the principle is what matters here. You're not seeing Sirius as it is. You're seeing Sirius as it was. You're looking back in time every single time you look up at a star. Vega, another bright star visible in the summer sky, is about 25 light-years away. If you're 25 years old and you look at Vega tonight, you're seeing light that left that star the year you were born. When that light began its journey toward Earth across the void of space, you hadn't been born yet. You didn't exist. Your parents might have been looking up at that same star, seeing light that left Vega 25 years before that, 50 years ago in total. The Vega you see tonight is a younger Vega, showing you what that star looked like a quarter century ago, not as it is right now. Betelgeuse, the red supergiant star in the constellation Orion, easily recognizable as the bright reddish star marking Orion's shoulder, is about 550 light-years away. It's one of the most famous stars in the entire night sky. The light you see from Betelgeuse tonight started its journey toward Earth in the year 1474, during the Italian Renaissance, before Columbus sailed to the Americas, when William Shakespeare was 22 years old and Michelangelo was about to be born. In 1474, the Byzantine Empire had fallen to the Ottoman Turks 21 years earlier. The printing press had been invented only about 20 years before, revolutionizing the spread of knowledge. Most of Europe was still emerging from the Middle Ages. The modern world as we know it didn't exist yet, and the light from Betelgeuse that you see tonight started its journey back then. It's been traveling through the emptiness of space for over 500 years, crossing the vast darkness between Betelgeuse and Earth to finally arrive at your eye tonight as you look up at the night sky. Betelgeuse is a particularly interesting example because it's a massive star nearing the end of its life. Stars like Betelgeuse don't last as long as smaller stars like the Sun. They burn their nuclear fuel much faster, living fast and dying young in cosmic terms. At some point in the relatively near future, astronomically speaking, within the next 100,000 years or so, Betelgeuse will explode as a supernova. When it does, it will shine briefly as bright as the full moon in our sky, visible even during the day. It will be a spectacular event, one of the most dramatic astronomical events visible from Earth in all of human history. But here's the unsettling thing. Betelgeuse might have already exploded. The explosion might have happened centuries ago, perhaps in the year 1600 or 1700 or 1800, but we wouldn't know yet. We wouldn't have any way of knowing. The light from that explosion would still be traveling toward us through space, moving at the speed of light, taking 550 years to make the journey from there to here. So if Betelgeuse exploded in the year 1700, we won't see it until about 2250. The star could already be gone right now, destroyed in a catastrophic supernova explosion that scattered its outer layers across space, and we'd still see it shining peacefully in the sky for centuries to come, completely unaware that we're seeing a ghost, an image of something that no longer exists in the present moment. Polaris, the North Star, the star that's guided travelers and sailors for thousands of years, is about 445 light-years away. When its current light began traveling toward us, the first permanent English colonies in North America hadn't been established yet. Jamestown wouldn't be founded for another 12 years. The Pilgrims wouldn't arrive at Plymouth Rock for another 26 years. William Shakespeare had just begun writing his plays. He'd written some of his early works, but hadn't written Hamlet, Macbeth, King Lear, or most of his other famous plays that we still read and perform today. The United States as a nation wouldn't exist for another 180 years. When that light from Polaris began its journey through space toward Earth, the world was fundamentally different from today. And tonight, that ancient light, that photon that's been traveling for 4.5 centuries, unchanged, moving at the speed of light through the void, finally enters your eye tonight as you look up at the night sky. You're connected across space and time by photons that have been traveling for 4.5 centuries, unchanged, moving at the speed of light through the void. Within about 20 light-years of Earth, there are about 130 known star systems. Some are single stars like our Sun, solitary in space. Others are binary systems, with 2 stars orbiting each other, locked in a gravitational dance. Some are even triple star systems, like Alpha Centauri, with 3 stars bound together by gravity. Understanding this stellar neighborhood helps us appreciate both the distances involved and the variety of stars that exist in our immediate cosmic backyard. Barnard's star is the second closest star system to Earth, after Alpha Centauri, about 6 light-years away. It's a red dwarf, much smaller and dimmer than the Sun, invisible to the naked eye. What makes Barnard's star particularly interesting is that it's moving toward us relatively quickly by stellar standards. It has the largest proper motion of any known star, meaning it moves across the sky faster than any other star seen from Earth over long periods of time. Over the course of decades and centuries, we can actually see Barnard's star change position relative to other background stars. It's measurably moving. In about 10,000 years, it will be closer to Earth than Proxima Centauri is now, becoming our new nearest stellar neighbor, our new next-door neighbor in the galaxy. But even at its closest approach, it will still be nearly 4 light-years away. The distances between stars are so vast that even when stars are moving toward each other through space, it takes thousands or tens of thousands of years for that motion to make any noticeable difference in the distance between them. Wolf 359, about 7.9 light-years away, is one of the fastest moving stars relative to the Sun, traveling at about 119 kilometers per second through space. That's fast for stellar standards. Most stars in our region of the galaxy move at speeds of a few dozens of kilometers per second relative to each other.
Wolf 359 is moving much faster than average, yet even at this speed, it's moving at only 0.04% of the speed of light. Stars move through space, but they move slowly compared to the vast distances between them. Even the fastest moving nearby star would take tens of thousands of years to travel just 1 light year.
Sirius, 8.6 light years away, is actually a binary system with 2 stars orbiting each other. Sirius A is a bright white main sequence star about twice the mass of the Sun. It's the brightest star in our night sky, partly because it's relatively close and partly because it's intrinsically quite luminous. Sirius B is completely different. It's a white dwarf, the dense remnant core of a star that exhausted its nuclear fuel and collapsed. White dwarfs are fascinating objects from a physics perspective. They're about the size of Earth, roughly 12,000 kilometers in diameter, but have the mass of a star, perhaps as much as our entire Sun. Sirius B has about the mass of our Sun compressed into a sphere about the size of our planet. This makes it incredibly dense, far denser than any material you could ever encounter on Earth. A teaspoon of material from Sirius B would weigh about 5 tons on Earth, as much as a large elephant. The 2 stars orbit each other every 50 years, locked together by gravity, each following an elliptical path around their common center of mass. The Milky Way, our home galaxy, is a spiral galaxy containing somewhere between 100 billion and 400 billion stars. That's a huge range of uncertainty, and it's actually quite difficult to count stars accurately in our own galaxy. We're inside it, which makes it like trying to count all the trees while standing in the middle of a dense forest. Dust blocks our view in many directions, making it impossible to see clearly across the galaxy. Dim stars, the red dwarfs that make up most of the stellar population, are hard to detect from a distance, and the galaxy is so large that we can't see all of it at once from our position out in one of the spiral arms. But the best estimates from astronomers suggest somewhere between 100 billion and 400 billion stars, with the most likely number being around 200 to 300 billion. Our Sun is just one of these stars, an ordinary yellow dwarf star of average size and brightness. There's nothing particularly special about our Sun from a galactic perspective. It's not the biggest, not the brightest, not the hottest, not the coolest. It's just a typical middle-aged star, one among hundreds of billions, located in one of the spiral arms about 26,000 light-years from the galactic center. 26,000 light-years. The light we see from the center of our galaxy, if we could somehow see through all the dust blocking the view, left the galactic center 26,000 years ago. When that light began its journey across the galaxy toward our solar system, humans were still living as hunter-gatherers in the Stone Age. Agriculture, the foundation of all civilization, hadn't been invented yet. There were no permanent settlements, no cities, no civilizations as we understand the term. People lived in small nomadic bands, following animal herds across the landscape, gathering wild plants, using simple stone tools to survive. Writing wouldn't be invented for another 21,000 years. Everything we think of as human civilization, everything from the first farms to the first cities to the first writing systems to all the ancient empires to the modern technological world we live in today, all of it has happened while light from the galactic center was traveling toward us through space. And that light, which left when humans were still primitive hunter-gatherers with stone tools, arrives at Earth tonight. The Milky Way is roughly 100,000 light-years across from one edge of the spiral arms to the other.
If you could somehow travel at the speed of light, which you can't because you have mass, it would take you 100,000 years to cross the galaxy from one side to the other. 100,000 years of traveling at the maximum possible speed in the universe. Modern humans, Homo sapiens, are about 300,000 years old as a species, so you could have started crossing the galaxy when the very first modern humans appeared in Africa, traveled at the speed of light continuously for 100,000 years, and you'd only be about 1/3 of the way across the galaxy today. That's how vast our galaxy is. The Sun orbits the galactic center at a speed of about 230 kilometers per second. That sounds fast, and it is fast by human standards. At that speed, you could travel across the United States in about 3 minutes. You could circle the entire Earth in just under 3 minutes. But even at this incredible speed, it takes the Sun about 225 million to 250 million years to complete one orbit around the galaxy. The last time the Sun was in its current position in the galaxy, dinosaurs were just beginning to evolve on Earth. The first dinosaurs appeared about 230 million years ago in the Triassic period. Since then, over the course of one complete galactic orbit, dinosaurs evolved from small creatures into the dominant life forms on the planet, ruled Earth for over 160 million years, went extinct 66 million years ago when an asteroid struck the Earth, mammals rose to dominance after their extinction, primates evolved, and eventually humans appeared. And the Sun has only just now returned to approximately the same position in the galaxy where it was when dinosaurs first evolved. One of the most exciting developments in astronomy over the past few decades has been the discovery of exoplanets, planets orbiting stars other than our Sun. Until 1992, we knew of only one planetary system in the entire universe, our own solar system, with its 8 planets orbiting the Sun. We suspected, we hoped that other stars might have planets too, but we had no direct evidence, no proof. Then, in 1992, astronomers detected the first planets orbiting another star, though it was a pulsar, a rapidly spinning neutron star, not a normal star. In 1995, they found the first exoplanet orbiting a normal Sun-like star, proving that planetary systems exist around other stars. And since then, the discoveries have exploded dramatically. As of 2024, we've confirmed the existence of over 5,000 exoplanets, with thousands more candidates waiting to be verified through additional observations. The TRAPPIST-1 system, about 40 light-years away, contains 7 Earth-sized planets orbiting a small red dwarf star. 3 of these planets are in the habitable zone, the region where temperatures could potentially allow liquid water to exist on the surface. This discovery, announced in 2017, was revolutionary. It showed that small red dwarf stars, the most common type of star in the galaxy, making up about 70% of all stars, can host multiple rocky planets. Since red dwarfs are so numerous, this suggests that rocky planets might be extremely common throughout the universe, perhaps numbering in the billions or trillions. The TRAPPIST-1 system is also remarkable because the planets are packed tightly together in a compact configuration. All 7 planets orbit closer to their star than Mercury orbits our Sun, but because the star is so small and cool, emitting much less energy than our Sun, 3 of the planets still receive about the same amount of energy from their star as Earth receives from our Sun, potentially making them habitable. If you stood on one of these planets, you'd see the other planets in the sky, some appearing larger than our moon appears from Earth. The planets are so close together that travel between them would be far easier than travel between planets in our solar system. But here's the thing about the TRAPPIST-1 system. When we observe it today through our telescopes, we're seeing it as it was 40 years ago, back in 1985. If there's intelligent life on one of those planets, life that's developed technology, and if that civilization started broadcasting radio signals into space, those signals would take 40 years to reach us, traveling at the speed of light. We'd be receiving signals today that were broadcast in 1985. And if we detected such a signal today, right now, and sent a response immediately, it would take another 40 years for our response to reach them. They'd receive our reply in 2065. That's an 80-year round trip for a single exchange of information, a single back and forth. You could ask a question as a young person and die of old age before receiving an answer. Let's think carefully about what communication really means when distances are measured in light years. This is one of the most challenging and sobering aspects of the scale of space, and it has profound implications for any future where humanity might try to establish settlements on other worlds or make contact with alien civilizations if they exist out there somewhere among the stars. Radio waves, the waves we use for communication, travel at the speed of light. They're electromagnetic radiation, just like visible light, but with longer wavelengths that our eyes can't detect. When we send radio signals into space, whether intentionally or just as leakage from our TV and radio broadcasts, they propagate outward in all directions at 300,000 kilometers per second. But even at this incredible speed, the fastest speed possible in the universe, communication across light years takes years. There's no way around it. Voyager 1, our most distant spacecraft, is now about 24 light hours away from Earth. That means there's a communication delay of about 24 hours each way. When mission controllers on Earth send a command to Voyager, that command takes about 24 hours to reach the spacecraft, traveling as a radio signal at the speed of light, covering about 25 billion kilometers through space. Any data Voyager sends back, any telemetry or information about its status, takes another 24 hours to reach Earth. There's roughly a 48-hour delay for any two-way communication. If something goes wrong with the spacecraft, if a system fails or some kind of anomaly occurs, Voyager must handle it autonomously, on its own, using its onboard computer systems. By the time engineers on Earth know there's a problem and can analyze it and send new commands to address it, 2 full days have passed. The situation on the spacecraft could have changed completely in that time. It could have entered safe mode, or depleted its power reserves, or any number of things could have happened. Now imagine trying to establish communication with a human settlement on a planet orbiting Proxima Centauri, 4.24 light-years away. You send a message from Earth asking how things are going, how the crops are growing, whether there are any problems that need addressing back home. That message travels at light speed for 4 years, 2 months, and about 20 days later, your message finally arrives at the colony. If they respond immediately, writing their response and sending it right back, their answer takes another 4.24 years to reach you back on Earth. That's over 8 years for a single exchange of information, a single back and forth. You could ask about their latest harvest and receive answer about crops that were eaten 4 years ago. You could ask how a sick person is doing and receive news of their death years after it happened, years after they were buried or cremated, years after everyone at the colony has moved on. You could send advice or help, but by the time it arrives at the colony, the situation will have changed completely. The problem might have resolved itself, or gotten worse, or evolved into something entirely different. Any kind of real-time communication, the kind of immediate back and forth we take completely for granted here on Earth, becomes absolutely impossible across these distances. Conversations would be painfully, frustratingly slow. Debates about decisions or policies would span decades. A diplomatic negotiation between Earth and a Proxima colony could take a century or more to resolve, with each party carefully considering their responses, knowing years would pass before hearing back, and years more before their reply could be answered. This has profound implications for governance and society that go beyond just inconvenience or annoyance. A colony 4 light-years away couldn't be governed from Earth in any meaningful sense. Any laws or directives sent from Earth would arrive years out of date. The political situation on Earth could change completely, utterly, between when a message was sent and when it arrived. Governments could fall, new ones could rise, entire political systems could change. By the time the colony receives orders from Earth, those orders might be obsolete, overturned by new governments or new policies that the colony won't hear about for another 4 years. The colony would need to be autonomous, completely self-governing, capable of making all its own decisions on everything from resource allocation to conflict resolution to emergency response. Because waiting years for approval or guidance on every decision would be utterly impossible. Nothing would get done. The colony and Earth would inevitably drift apart culturally over time, developing their own customs, their own ways of life, their own solutions to problems, their own values and priorities. They'd be connected by messages from the past, letters from another time, but unable to maintain the kind of immediate, ongoing connection that holds societies together and keeps them unified. Over generations, perhaps just a few generations, they might become so different that they'd barely recognize each other anymore. They'd share a common origin, a common history up to the point of separation, but from that point forward, they'd diverge, evolving separately like species isolated on different islands, adapting to their local conditions and circumstances. For more distant stars, it gets worse, even more challenging. A settlement 10 light-years away would have a 20-year round-trip communication time. Messages you send to your children living there won't reach them until they're adults, possibly with children of their own. Their responses would return when your grandchildren are grown, when you yourself are old or possibly dead. You could exchange letters across the decades, sharing news and staying in touch in some abstract sense, but you couldn't have a relationship in any normal meaning of the word. You'd be communicating with people across time as much as across space. A civilization 100 light-years away would have a 200-year communication delay for a round trip. You could send a message, and neither you nor your children nor your grandchildren nor even your great-great-grandchildren would live to see the reply. Only your great-great-great-grandchildren, living in a world you could barely imagine, might hear back from that distant civilization. The conversation would span generations, with each generation sending messages to strangers they'd never meet, people separated not just by distance, but by time, receiving messages from people long dead.
If you could travel close to light speed, something truly strange happens with time due to Einstein's time dilation effect. This has been confirmed by countless experiments and is as solidly established as any fact in physics. As you approach light speed, time slows down for you relative to stationary observers. The faster you go, the more extreme this effect becomes. This isn't just clocks running slow or some kind of mechanical effect. This is time itself passing more slowly for you. Your heartbeat, your thoughts, your aging, your metabolism, everything happens more slowly from the perspective of someone who's not moving with you. Though from your own perspective, sitting in your spacecraft, everything seems completely normal to you. Time passes normally for you. It's everyone else's time that seems to be passing quickly, racing forward. Imagine a spacecraft that could somehow reach 99.9% of light speed. Not quite light speed, but very, very close. You board this spacecraft and travel to a star 10 light-years away, then turn around and come back home to Earth. From Earth's perspective, watching from the ground through telescopes, this journey takes about 20 years. 10.1 years to get there at 99.9% of light speed, and another 10.1 years to come back. Anyone watching from Earth would see your spacecraft take about 20 years for the round trip. But because of time dilation at this extreme speed, you would age much less than that. At 99.9% of light speed, time passes about 22 times slower for you than for people on Earth. So while 20 years passed on Earth, you would only experience an age about 11 months, less than a year. You'd step off the spacecraft having aged less than a year, while everyone you knew on Earth aged 20 full years. Your younger sibling might now be older than you. Your children, if you had any, might now be adults, older than you in appearance and experience. You've effectively traveled into their future. You left Earth in, say, 2050, experienced 11 months of travel time aboard your spacecraft, and returned to Earth in 2070. For you, it felt like less than a year passed. For everyone else, 2 full decades went by. Friends aged, children grew up. The world changed, technology advanced, politics shifted, culture evolved, and you missed all of it, experiencing only 11 months, while everyone else lived through 20 years. If you traveled even faster, at 99.99% of light speed, the effect becomes even more extreme. You could travel to a star 100 light years away and back. From Earth's perspective, this journey takes over 200 years, but from your perspective, due to the extreme time dilation at this speed, the journey might take only a few years of your subjective experience. Maybe 3 or 4 years of your life spent aboard your ship, living through just a few years aboard your ship, reading books, exercising, maybe sleeping in some kind of suspended animation for part of the journey. But when you return to Earth, over 200 years would have passed. Everyone you knew would be long dead, gone for generations. The world would be completely different, transformed. Political systems would have changed, possibly multiple times. Technologies you couldn't even imagine would exist. Languages might have evolved to the point where you struggle to understand modern speakers. Culture, society, everything would be foreign to you. You'd return to a future Earth that would be as alien to you as if you'd traveled forward by 2 centuries. Let's zoom out even further now, to truly cosmic scales. The observable universe is the region of space from which light has had time to reach us since the Big Bang. The universe is about 13.8 billion years old. Light has been traveling toward us for all that time, since the very beginning. But here's something interesting. The observable universe is actually larger than 13.8 billion light-years in radius, because the universe has been expanding while the light was traveling toward us. Space itself has been stretching, carrying distant objects farther away even as their light traveled toward us. The observable universe is about 46.5 billion light-years in radius, making it about 93 billion light-years across, from one edge to the other. This is the distance to the edge of what we can possibly see, the cosmic horizon. Beyond this distance, space has been expanding so fast that light from those regions hasn't reached us yet, in fact, never will, due to the acceleration of cosmic expansion. There's a cosmic horizon beyond which we cannot see, not because we don't have powerful enough telescopes, but because the light simply hasn't had time to reach us yet, given the age of the universe and the rate at which space is expanding. Within this observable universe are an estimated 2 trillion galaxies. Each galaxy contains anywhere from billions to trillions of stars. If you multiply it out, doing the rough calculation, the total number of stars in the observable universe is estimated at around 200 billion trillion. That's a 2 followed by 23 zeros. And we know from observations and statistical studies that most stars, probably the vast majority, have at least one planet orbiting them. So there are probably similar numbers of planets in the universe, maybe even more, since many stars have multiple planets. The universe is absolutely filled with worlds, more worlds than we could ever count, more worlds than we could ever visit even if we had unlimited time and unlimited technology and could travel at the speed of light for billions of years. At the largest scales, the universe has structure, patterns in how matter is distributed. Galaxies aren't randomly scattered through space like grains of sand thrown in the air. They're organized into clusters, groups of dozens or hundreds of galaxies held together by their mutual gravity. These clusters are organized into superclusters, massive structures containing multiple galaxy clusters spanning hundreds of millions of light years. And the superclusters are arranged in filaments, enormous thread-like structures stretching hundreds of millions of light years across space, the largest structures in the known universe. Between these filaments are vast voids, regions with very few galaxies, empty spaces that can be hundreds of millions of light years across. The universe at the largest scales looks almost like a sponge or a foam, with matter concentrated in thin sheets and filaments surrounding enormous empty voids. The universe is expanding, and it has been since the Big Bang 13.8 billion years ago. Space itself is stretching, growing, creating more space between distant objects, carrying galaxies apart like raisins in rising bread dough. This isn't just galaxies moving through space like cars on a highway. Space itself is stretching, creating more distance between objects. For nearby objects, this expansion is negligible, completely overwhelmed by other forces. The space between Earth and the Moon isn't expanding in any meaningful way. Gravity holds Earth and Moon together far more strongly than cosmic expansion tries to pull them apart. The space within our solar system isn't expanding measurably. Gravity holds the planets in their orbits around the Sun. The space within our galaxy isn't expanding. Gravity holds the stars together in the Milky Way. But on larger scales, between galaxies, and especially between galaxy clusters separated by hundreds of millions or billions of light years, the expansion becomes significant and eventually dominant. Distant galaxies are receding from us as space expands between us and them. The farther away a galaxy is, the faster it's receding from us. This isn't because the galaxies themselves are moving through space at high speeds. They're sitting relatively still in their local regions of space. But the space between us and them is expanding, and the cumulative expansion over vast distances adds up to high recession speeds. For galaxies that are far enough away, billions of light years distant, space between us and them is expanding faster than light can travel through it. This doesn't violate the cosmic speed limit, the rule that nothing can move faster than light, because the galaxies themselves aren't moving faster than light through space. They're essentially stationary in their local space. But the space itself between us and them is expanding so rapidly that the distance between us grows faster than light could traverse it, faster than photons can close the gap. It's like trying to walk forward on a treadmill that's moving backward faster than you can walk. You're walking at your normal speed, moving your legs normally, but you're moving backward relative to your starting point because the treadmill is moving backward faster than your forward walking speed can compensate for. This means there are regions of the universe, perhaps most of the universe, that are moving away from us so fast that light from those regions will never reach us. Not in a billion years, not in a trillion years, not ever. There's a cosmic horizon beyond which we cannot see, not just because the light hasn't had time to reach us yet, but because it never will reach us. The expansion of space is carrying those regions away faster than light can close the gap between us. We are fundamentally, irreversibly cut off from those regions of the universe. They exist, but we can never see them, never reach them, never communicate with them. They're beyond our cosmic horizon forever. Given the vast number of stars and planets in the universe,
Given that the universe is 13.8 billion years old and had plenty of time for life to evolve, given that life arose on Earth relatively quickly after conditions became suitable, within maybe a billion years or so, it seems likely, almost certain, that life should exist elsewhere in the universe, perhaps even intelligent, technological life capable of building civilizations and spacecraft and radio transmitters. And yet, despite decades of searching, we've never detected any signs of alien civilizations. No radio signals carrying messages or even just the electromagnetic noise of alien technology. No laser pulses sent deliberately to get our attention. No megastructures like Dyson spheres or ring worlds that would be visible from light years away. No signs of large-scale engineering projects modifying entire star systems. Nothing. The universe, as far as we can tell, appears to be silent, empty. We seem to be alone, at least in our cosmic neighborhood. This is called the Fermi paradox, named after physicist Enrico Fermi, who famously asked during a lunch conversation, "Where is everybody?" If intelligent life is common, if technological civilizations arise regularly throughout the galaxy, where are they? Why haven't we detected them? Why haven't they visited us, or at least sent us a message? The light year might be part of the answer to this paradox. The distances between stars, measured in light years, are so vast that they present enormous, perhaps insurmountable barriers to communication and travel. Our radio signals, our television broadcasts, our radar installations have been leaking into space for about a century now, since humans first invented radio technology in the early 1900s. These signals travel at light speed, spreading outward in an expanding sphere around Earth. They've now reached all stars within about 100 light-years of Earth. That sounds like a lot. 100 light-years is a huge distance by human standards, incomprehensibly vast. But the Milky Way galaxy is 100,000 light-years across. Our signals have covered a sphere 100 light-years of radius in a galaxy 100,000 light-years across. That's a tiny, tiny fraction of the galaxy, an almost invisibly small region. We've barely announced our presence to our immediate cosmic neighborhood. And even those signals that have traveled 100 light-years are getting weaker as they spread out, dispersing. The farther they travel, the more they disperse, spreading out over a larger and larger sphere, diluting like a drop of ink in an ocean. By the time our TV broadcasts reach a star a few dozen light-years away, they're so faint they'd be almost impossible to detect above the background noise of space. Even with very sensitive equipment, any alien civilization trying to detect us would need extremely powerful radio telescopes pointed in our exact direction, tuned to the exact right frequency, listening at exactly the right time to pick up our weak signals against the cosmic background noise. So what does all this mean for us? How should we think about light years in our daily lives here on Earth? For most people, most of the time, light years don't affect daily life at all. You don't need to think about Proxima Centauri being 4.24 light years away when you're deciding what to have for breakfast, whether to take an umbrella because it might rain, or which route to take to work to avoid traffic. These cosmic distances don't directly impact your day-to-day existence. But there's real value in occasionally stepping back and contemplating these scales, thinking about the vast distances between stars and our place in the cosmos. It provides perspective on our place in the universe, on what matters and what doesn't. When you realize that Earth is a small planet orbiting an ordinary star, and that the nearest other star is over 4 light-years away, and that our galaxy contains hundreds of billions of stars, and that there are trillions of galaxies in the observable universe, it changes how you see things. It shifts your perspective fundamentally.
Your problems, whatever they are, exist on one tiny planet in a vast universe. That argument with a friend, that stress at work, that anxiety about the future, that disappointment, that frustration,
all of it happens on one small world orbiting one ordinary star in one galaxy among trillions. The nearest star doesn't care about your problems. The galaxy doesn't notice your existence. The universe continues its slow evolution over billions of years, completely indifferent to human affairs, to our wars and politics and dramas. This isn't meant to diminish your experiences or suggest that your problems don't matter. Your life matters to you, and that's what's important ultimately. Pain is real pain. Joy is real joy. Love is real love. These things are real and important regardless of the scale of the universe. But sometimes, when things feel overwhelming, when you're stressed or anxious or worried about something, it can help to remember the scale of the universe. It can help to step outside yourself mentally and remember that you're living on a small planet orbiting an ordinary star in a vast cosmos. From that cosmic perspective, your problems are temporary, local, small. Not unimportant to you, but small in the grand scheme of things, contained, manageable. This too shall pass, as the old saying goes. Whatever you're dealing with, whatever challenge or difficulty, it's happening in a tiny corner of space and time, and it will eventually resolve one way or another. There's also something beautiful, something almost spiritual about understanding light years. When you look up at the night sky, you're not just seeing points of light scattered randomly across the darkness. You're seeing stars that are light years away. You're seeing photons, tiny particles of light that have been traveling through the emptiness of space for years or centuries or even millennia to reach your eyes in this moment. You're connected to those distant suns across vast distances of space and time by light itself. You're part of the universe, made of atoms forged in stars billions of years ago, looking up at other stars, understanding your place in the cosmic order. Every star you see has a story. Some are young, just forming from collapsing clouds of gas and dust, beginning their lives as nuclear furnaces, fusing hydrogen into helium. Some are middle-aged, like our sun, steadily burning hydrogen in their cores, stable and long-lived, shining steadily for billions of years. Some are old, approaching the end of their lives, having exhausted their nuclear fuel, destined to either become white dwarfs, cooling slowly over trillions of years, or to explode as supernovae, scattering their atoms across space to be recycled into new stars and planets, and potentially life. Tonight, we've explored the light year in depth, really in depth. We've looked at what it means, how it's measured, what distances it represents, and its implications for understanding the universe and our place within it. We've taken a journey from the familiar scales of our everyday life, the distances we can walk in minutes or drive in hours, to the almost incomprehensible scales of cosmic distance measured in light years. A light year is 9.46 trillion kilometers, the distance light travels in 1 year, moving at 300,000 kilometers per second continuously. It's the unit astronomers use because kilometers and other terrestrial units of measurement become completely unwieldy when dealing with cosmic distances. When you're measuring distances to stars and galaxies, you need a unit that's large enough to make the numbers manageable while still being based on something physical and measurable, something real. The nearest star to our Sun, Proxima Centauri, is 4.24 light-years away. That's the closest stellar neighbor we have, and it's still so far away that with current technology, it would take thousands of years to reach it. Our galaxy, the Milky Way, is roughly 100,000 light-years across. To cross our own galaxy at the speed of light would require 100,000 years of continuous travel. The observable universe is 93 billion light-years across. containing an estimated 2 trillion galaxies, each with billions or trillions of stars. When you look at stars in the night sky, you're not seeing them as they are right now in this present moment. You're seeing light that has traveled for years, or centuries, or even millennia to reach your eyes in this moment. You're literally looking into the past every time you gaze up at the stars. Sirius, the brightest star in the night sky, is 8.6 light-years away. You're seeing it as it was 8.6 years ago. Betelgeuse, the red supergiant in Orion, is about 550 light-years away. You're seeing it as it was during the Renaissance, over 5 centuries ago. A light-year connects distance and time in a fundamental way, showing that in our universe they're unified aspects of space-time rather than separate, independent concepts. The speed of light is a fundamental speed limit built into the structure of the universe itself. Nothing can travel faster than light. This isn't a technological limitation we might overcome with better engineering someday. It's a law of physics, an ironclad rule, a consequence of how space-time works at the most fundamental level. This means that distances measured in light-years represent real barriers to communication and travel, not just engineering challenges. Stars that are light-years away are separated from us not just by space, but by time itself. Even traveling at the speed of light, which is impossible for anything with mass, you'd still need years to reach nearby stars, and millions or billions of years to reach distant galaxies. Despite these vast distances and fundamental barriers, despite the isolation imposed by the light year and the speed limit of the universe, we've learned an enormous amount about the cosmos. We've mapped billions of stars, measuring their distances with ever-increasing precision. We've detected thousands of exoplanets orbiting other stars, some of them potentially habitable. We've observed galaxies billions of light-years away, seeing them as they were in the early universe, just after the Big Bang. The light year has been our fundamental tool for measuring and understanding these cosmic distances, for mapping the universe and determining our place within it. So the next time you're lying in bed at night, maybe having trouble falling asleep, and you look out your window and see stars in the sky, remember what you've learned tonight. Those points of light are not just decorations on the celestial sphere. They're distant suns, massive balls of fusing hydrogen, each one potentially hosting its own system of planets and moons. They're light-years away, separated from us by distances so vast that the light entering your eye right now has been traveling for years or centuries or even millennia to reach you in this moment. You're connected to those distant stars across vast distances of space and time, linked by photons that have crossed the cosmic void to reach you in this moment. And that connection, that link across space and time through light itself, is something profound and beautiful. The universe is vast beyond our ability to fully comprehend. You are small, a single person on a single planet, orbiting a single star in a single galaxy among trillions. But you're here, and you can understand, at least conceptually if not intuitively, what a light year really means. You can grasp, even if imperfectly, that the universe is measured in these vast units, that space is filled with distances that dwarf anything in human experience. And that understanding, that ability to comprehend your place in the cosmos, is extraordinary. It's what makes us human, what separates us from other life on Earth. If you enjoyed this peaceful journey through space and time, exploring what a light year really means, you might enjoy learning about other cosmic mysteries. There's so much more to discover about our universe, so many more questions to explore as you drift off to sleep. Sweet dreams, and may the stars light your way through the night. Good night.